understanding me or with my English, please raise your hand or shout or just tell me. And so, like it said, I would like to speak about sustainable insulation for power cables. And sorry, I need just to move a little bit that I can see. Yeah. So, and first of all, a slight warning, if you are trying to work on that subject, there is a minefield of patents around there. So please be careful because there are a lot of patents around. I'm not mentioning them all, but there are a lot. So in principle, when we're speaking about sustainable cable insulation system, we're speaking about semicons and insulations. However, I will focus in this presentation mainly on the insulation system because there are more data available, and the semicons, nobody really likes to work with them because they are black and you get dirty fingers. So looking at thermoplastic materials, they are not that new. So we have LDPE that has been used, for example, in France and Germany. In France, even up for 400 kV. Their limitation was there that it had 70 degrees conductor temperature and 150, 160 degrees short circuit temperature. So you were limited in conductor size. The HDPE also has been used, for example, in France for up to 400 kV. And both of them, these cables are, according to my information, still in service. Ultra high molecular weight polyethylene, also thermoplastic, has used mainly in the USA with, I would say, mixed success, but mainly in the medium voltage area. Then we have polybutene 1. This is a newer material. It's under test at several locations, and there might be something coming out soon. Then also for medium voltage, soft PVC has been used for up to 20 kV, for example, in Germany. The cables are still in their network. The limitation for higher voltages there is the loss factor, and also the conductor temperature is 70 degrees. In nuclear reactors, it's used as a cross-linked FR version, according to my knowledge, but I'm not going too far into this. Just to give you some background of other thermoplastic materials. When we're speaking now about polypropylene, it's not a new material. It has been developed in the 50s by Natta in Italy, and it has been already used in electrical or cable application in, for example, in capacitor films for a long time. It has been also used as a coating polymer for paper, laminated paper cables, so-called PPLP cables, in several cable projects, for example, and now it's coming my pronunciation, in Japan called Kai channel. This is a 500 kV project, and it was also used in Westlink, connecting the England with Scotland, if my memory is right. This is a 600 kV, also HVDC cable. Speaking now a little bit about chemistry, I know that a lot of you are electrical engineers. So polypropylene in principle is the blue spots that you see on the bottom. Mainly you're speaking about a homopolymer. So you have hydrogen, so you have carbon, electricity, and then you have a carbon sticking out. This is a simplified image of polypropylene. Mainly for cable application, we're speaking about something different. We're speaking about copolymers. That means you copolymerize a polyethylene with a second polymer, ethylene, hexane, or butane, and you get a random copolymer or a block copolymer. Random means that randomly you have the copolymer distributed in the polymer chain. A block copolymer, it's actually, there's a block inside the polyethylene chain that gives you specific different properties than with a random polymer. I will not speak too much about chemistry. So I know that you most are electrical engineers, so therefore I don't want to broaden you up. If you have other questions, still please ask them at the end. So the market situation actually at the moment, and I'm just highlighting the most important solution at the moment. We have compounds, we have different players on the market there. We have compounds with a liquid voltage stabilizer. So you have a polypropylene compound. It's not a pure polypropylene, it's actually always compounded. And once there's a liquid voltage stabilizer in, another one is claiming that they have an aromatic voltage stabilizer in it. And they are compound space with different polymer together with polypropylene. At the moment, last time I counted, we have at least 7 different players on the market who have a polypropylene solution. And the big highlight where everybody is watching now was 2 projects in the corridor projects in Germany, giving to the Brisbane company called P-Laser for 525 kV DC. I think this is the biggest challenge that we will see on the market, not only for polypropylene, but also for all the rest around that. So, like a little bit summarizing, XLPE is on the market since the 70s. So even I was barely at school during that time, but it's dominating now for low voltage, medium voltage, high voltage, and extra voltage. And there's no question, it has a very good market success. It's reliable as in the market. Since 3 decades, roughly, XLPE has been also used for HVDC with some mixed success. There were some hiccups, but not too much with the cable, mainly with the accessories. And thermoplastic polypropylene has been introduced, I think, in 2009 from, at that time, Pirelli, now Brisbane, under the trade name P-Laser. And since then, I think more than 50,000 system kilometers in medium voltage have been installed worldwide. Worldwide, I mean mainly from Brisbane, mainly in Europe. The advantages are they have a higher operating temperature, it's fully recyclable, it has a shorter lead time in production, you don't need to degas the material because there's no cross-linking, and recently it has been introduced in several standards. Show you a little bit the highlights, the differences between the thermoplastic materials. You have the properties compared to from PP compared to LDPE and HDPE. So polypropylene is more stiff than LDPE, but more flexible than high density polyethylene. The tensile strength is higher. The density is lower. The shrinkage is also lower, and the thermal expansion is also lower. So you have less expansion when you heat up the cable or shrinking down. So you have it's less. The density is lower, gives you I would say a minimized advantage because you need a little bit less material when you extrude the cable. Comparing now the differences in polypropylene, these are typical values, not exactly exact values. So you have the homopolymer, random copo, and block copo. The tensile strength is slightly different. The density of the copos is a little bit less because you have a better assortment of the chain. The shrinkage is in the same area. The linear thermal expansion is for the copos are a little bit higher. Tracking index is the same, and electrical strength is there's also no difference. When we speak about the differences, so when we're speaking about recyclability, there will be a, I just have to highlight you, there will be a presentation at a local secret where we look at low voltage recycling material inside cables. Till now, the recyclability is not being, the material is not being used in cables, but for other applications. It's easier to recycle because there is no cross-linking. So you can melt the material after production again as much as you want. The other advantage, and I think that's going more in when we're speaking about DC and high voltage application, since you don't have any cross-linking, you don't have any byproducts during production. That means you don't need to do any degassing. It's not such a big advantage for medium voltage, but when you're speaking about DC application, it gives you a clear advantage because you can produce the cable and you immediately can continue, and the electrical properties do not change too much over time, except due to aging. The advantage is also you can make shorter lengths. So if a utility is coming to the cable maker and wants to have 500 meters of cables, he will not get the middle finger, so you can actually produce it without you producing too much scrap. The other thing is, again, no curing, no degassing. No curing means you don't have to heat up the cable to reach 180, 200 degrees. You immediately can cool it down. So that means the place or space that you need for the production area is significantly smaller. Until now, I was told that the accessories that you can use for polypropylene, are used for polypropylene cables, are the same that you're also using for XLPE cables. So there is no difference in accessories that I'm aware of. People can teach me different, but this is what I'm aware of. Also, due that you don't have any curing, your production lengths can be longer because you don't have any scorch. That means no pre-cross-linking of the material. Also, on the other hand, is also when you're making a factory joint, you can, this is easier because the factory joint doesn't have to be cross-linked. You just make it thermoplastic. Tandemizing, for medium voltage at least, you can make the insulation, also it means the cable core, the screening and the jacketing in one shot. The space charges for HVDC, the space charges in a polypropylene are lower, and I will come back to that later. The thermal performance is, the operating temperature can go up to 110 degrees. Emergency temperature, like XLPE, for up to 130. Overload temperature also in that area, and you still have a very good mechanical properties. Everything is nice, but naturally there are also some disadvantages or some addressing the, how should I say, some negative points that should come up there, because not everything is bad. That would be an easy way. So polypropylene has a lower temperature, also a higher temperature, low temperature brittleness temperature. That's a difficult thing as well. So that means it's get brittle at higher temperature than crosslink LDPE. There are also some concerns raised about the cleanliness of the product and about the thermal conductivity compared to XLPE. I must say, to the latter, I will come to that, it has also something to do with the density. So low temperature brittleness. The issue was here, the test we made, you might ask yourself, why did we only go down to -20 degrees? That was at that time the customer request. In that country, the cables were installed only at -20 degrees. I know that there are certain countries where the temperatures can be lower, like certain countries require -70, but I'm 100% sure at -70, you have other problems actually when you install cables than just an unflexible insulation. So what's up here is the low line, the green one is XLPE, and then you have different polypropylene compounds, the blue and the red. I hope you have the same colors that I have. And on the top there is a high density polyethylene commercial jacketing compound. Measured, the flexibility is measured according to ISO around that temperature range. And we also used as a comparison the PVC jacketing compound. And as you can see, we couldn't measure it at -20 degrees because it breaks at lower temperature. So if you have a PVC jacketing, the brittleness of polypropylene is actually not an issue, or the unflexibility of or hardness of polypropylene is not an issue. Also, when you compare to what's normally used, at least in Europe, high-density polyethylene, we have learned in the practical way that the sheeting compounds are, or when we speak about the jacketing compounds, are significantly stiffer than actually polypropylene. However, as you can see here, these two nice guys, they made a test. So what we did, we put a cable, we put it around the drum, it's 15 L/D. We left it for 24 hours at minus 20 degrees, and then we unwinded the cable, and afterwards we made a AC breakdown test and a partial discharge measurement, and none of these tests showed any significant damage to the cable. At minus 20 degrees, it was quite stiff, but we managed it so you can handle and install the cable at minus 20 degrees. So low temperature is not an issue. Thermal conductivity, the other subject, is, like I already said, the thermal has also something to do with the density. So here's a comparison, and I'm trying to get this window. Sorry. So here's a comparison of XLPE with 3 different polypropylene compounds. The red one with the deep drop in here, or change here around 90-100 degrees, is the XLPE, and the green and the magenta one, no, sorry, the green and all the other ones are polypropylene compounds. The blue one is a commercial that is in service. The green and the magenta one are polypropylene compounds under development, where we try to improve the thermal conductivity. The difference between the blue one and the XLPE will result in a 6 Kelvin higher conductor temperature at the same load. This was also confirmed in practice at 90 degrees. So there are solutions there, but it needs to be commercialized and needs to be further evaluated. The other thing is the cleanliness. So one of the cleanliness contaminations that you have in polypropylene, because it's produced via a catalyst, are catalyst residues, which is a silica, and a couple of you might heard about nanomaterials. So the advantage of this is that the silicium or the silica is very well dispersed inside the polymer, and I think it's one of the best nanocomposites that you can have, and silica is actually known to be a water retardant additive. There are also other catalysts that are used, and I had a discussion a couple of weeks ago, and most of them are also used has been evaluated for HVDC applications. The other particles that can be in is we have the advantage with polypropylene because we are thermoplastic, so that we can filter it down to 500 mesh. So in principle, we can remove nearly all or a lot of contaminations out of the material. Here's a test that we have done. We looked actually what contamination is in the cable, and we compared polypropylene compounds with XLPE compounds. On the left-hand side, so you see a commercial XLPE compound, 2 commercial XLPE compounds that are in the market, and the one XLPE1 is just standardized to 100 in each contamination class, and the other ones are put in relation. So at least in that test, I clearly can say that polypropylene is in the same contamination range than a medium voltage XLPE compound. We also look inside the cable. We're looking at a company, something is ultrasense, so there's a trademark missing. This is also a trademark, and this is under evaluation, and this is a chance to look actually inside the cable to overcome the disadvantage, because it's very difficult to make a hot silicon oil test on polypropylene insulation. Speaking another thing about contamination, And there are comparisons done, water treating, which is known that contaminations can create water trees under certain tests. So here's a comparison done from polypropylene with an LDPE cable grade. As you can see, it's not that new. It has been published in 1987. So that was before I was starting working in the cable industry. And polypropylene there is better than polyethylene in this specific test. We made more comparison there. We made a water treat test at ELMAT. This is the University of Bucharest. And also here you can see that the polypropylene, the compound, had the same water treat retardancy than commercial water treat retardant compound. Once again, the density and the relative length was put at 100% in relation, and the PP has less water trees, that means less contamination, and only a slightly higher water recourse rate. Commercial compounds are up here. Cable tests have been done at Labo Elec, which is the test in Belgium, and they couldn't find any water trees in that test. Also, like I said, the leader is Prismian. When we're doing a 2-year test according to the harmonized CEDELEC, European spec harmonized document HD 605, HD 620, and they compared EPR with polypropylene. It has the same water tree behavior on a cable than an EPR in that specific test. What we also did, and now you might be surprised, this looks like a hot set test. This is a test that we have done and we have presented some years ago at Secret in a session in Paris. That was before Corona. So we have, that's the new time counting there. And we compared polypropylene with XLPE. What we did, we didn't go at the normal test. Heat elongation is done at 200 degrees, 15 minutes. So we did it at 135 degrees and a longer time. And that has been done 42 days. And the elongation of polypropylene or XLPE were in the same range over time. And the surprising thing that was surprising even for me was that the polypropylene even moved back when we removed the weight. So the elongation was not permanent. Why? I still don't understand. Looking now more about cable data. Rosette is a commercial name by one of the machinery suppliers. So cable data are showing the same electrical properties of polypropylene than with XLPE. And what was also done in a comparison test is a 2-year test was done under different aging temperatures. So the red on the left-hand side is 23 degrees, which is the old UniPD test requirement. 40 degrees is the HD 605 test requirement in the 2-year test, and 90 degrees is the test requirements that is done in North America by the IEEE. What was compared here were 2 different XLPE compounds, 2 different polypropylene compounds, and there are also more EPRs, but only for the sake of clearance. I didn't put too many things in there. So as you can see here, there are different performance values after 2 years when you're having polypropylene or when you're having XLPE, and also with EPR. What I'm saying is you have to be careful because the water is migrating in a different way inside the cable. Impulse breakdown and here is the comparison between XLPE and 2 different polypropylene compounds. The aging was done according to the guide that 1407 and HD 605. We used impulse, and here you can see that afterwards the cable is still behaving well, but also showing here that you have differences depending which test you're using. So impulse, that was by the former Steve Jobs, he was always insisting that you should make impulse breakdown and not AC breakdown of water to EH cables. Looking at type test results, here you're having China. Certain people are able to read that perfectly. For the people who are not so perfect in Chinese, there's an English translation below there. And in principle, the most important thing what you can look at is the PPPPPPP or non-applicable. So the test passed the application for a 15 kV cable. And here more interesting, electrical type test according to IEEE 6502. And here also show you the results, and it passed perfectly the type test over there. More important thing, I'm rushing a little bit with pictures through it. A short circuit test at 250 degrees. I must honestly say that was my biggest concern. What is happening with that? And also here at 250 degrees, the cable passed the test. As the 500 cable is bent here, you put the circuit, you put several shots of short circuit into it, and the cable should be still intact after the test. And that's there. Now looking more into the development, because naturally people looking in the future. And here an overview about polypropylene, and added to this different parts of LDPE 10, 30 to 50, high density polyethylene, same range, polyolefin elastomers, different ones, and it's there, and then pure polypropylene, and on the right hand side you see pure XLPE. And as you can see, by adding other materials to polypropylene, you can improve the pure polypropylene, the electrical properties in AC breakdown test over there. So yeah, I just need something to do. Additionally, looking now again in mixing up, and there should be a slide before. Sorry, there is a slide missing. It somehow disappeared when I prepared it. At a different temperature, looking at the AC breakdown tanks of polypropylene mixed with syntactic polypropylene. So just mixing isotactic and syntactic polypropylene up to 45% syntactic polypropylene. And here you can see the differences at different temperatures. So you have to be careful. It's not always where and how you're doing the test. You cannot generalize that addition of another polymer will give you an advantage. There's always an optimum, or if I put it the other way around, an optimum at a certain temperature that you can add, and at a certain time you're going in the worst direction. Just looking a little bit at my time. And again, breakdown test. Here again, polypropylene with mixtures. You can see that the blue one in the middle here, or better say over here, and the improvement. So polypropylene with only 10% of the second polymer gives you actually the best advantage in breakdown strength. And here it was a PP copo with an elastomer. That was a little bit about AC application. And now we're going into the DC, which I think is actually more sexy at the moment. So the basic is the threshold for space charges for polypropylene is significantly higher than for XLPE. This has been evaluated at several universities in several tests comparing PP compounds with XLPE compounds, and in average you roughly have 7 in a field of 7 kilovolt higher you create space charge. Plus and minus, there's a different value. Other tests you comparing a polypropylene compound with commercial DC XLPE compound. About aging, here we measured the tangent delta over time. You can see a big spread, but overaging, because the issue is you creating carboxy group, which are polar, and that means you have an increase in tangent delta. The issue here was also that we had the first break with XLPE, that we had the first breakdowns roughly after 306, 1 year and some months in that test. There are new tests set up, and they hopefully will report it soon. Looking at the conductivity, which is a very sensible thing to measure. I personally have never done it. I only saw the result, and I must say this is an optimized length. It's normally more like a line made by a 150-year-old man, or after you have been drinking for a fortnight and you are now sober. And so it's not such a smooth line. There's far bigger variation in that. However, XLPE is going up over temperature, where polypropylene is staying more stable when you have comparing the conductivity, the charges. Space charge here now measured with TSM. Also here, polypropylene with XLPE, you can see that polypropylene is far more stable and less sensitive to space charges than XLPE. When we're coming now to that, naturally here also people have looked into polypropylene compounds, mixing different polymers together. In this test, they only mix different polypropylenes together: isotactic polypropylene, syntactic polypropylene, and atactic polypropylene. The atactic, stayed always at 5%. So what was varied here was an increase of syntactic polypropylene, and naturally the isotactic polypropylene was then replaced, and the results are here below. So also here you have an optimized pink one in the middle is there. So you also have an optimized value. So at first you are decreasing the electrical property, the DC breakdown, and then you can increase it again if you're going over a certain threshold. The conductivity, and I fully agree, I hope this is very difficult to see depending on what screen you have. The thermal conductivity of the material using different polypropylenes, other polypropylene compounds, an isotactic polypropylene, and then it's compared with a polypropylene ethylene copolymer, polypropylene butylene copolymer, and you're getting different conductivity, the charge density. It could not be conductivity. Sorry, I have to correct myself. This is space charge measurement. I'm very sorry about that. So you can see that you have differences again on the compound, and about the compound depending which you're using. So be careful, ask the specific questions when you see presentation. I have several presentations also for XLPE, where I'm saying XLPE is not XLPE. For polypropylene is getting even more complicated. Again, comparing here now is conductivity. The conductivity of polypropylene with XLPE with different addition of material, and this is the same material that was highlighted before. That you can see also here that you vary the conductivity, that it's not stable depending on that. So there is no clear line. You always has an optimum or a minimum during that. And I fully agree, this you cannot see at all. So I hope when you're having it there, so we're comparing here on the left-hand side polypropylene. The tests that were done here were adding different additives to it: magnesium oxide, titanium oxide, zinc oxide, and aluminum oxide. 1 PHR, 3 or 5 PHR. PHR, for the people who don't know it, it's parts per 100 rubber. This is coming from the rubber industry. So you using the whole total polymer as 100%, and then you just adding 1% or up to 5% of this material, of the additive to it. The space charge were measured at 60 kilovolt, and it was done as a nanocomposite and showing the differences of different additives to the space charge development to virgin polypropylene. Same thing here. I think it's easier to see because it just shows the space charge development. So comparing to this, here again, it just shows it at different temperatures and how the space charges are developed over at different temperatures in the same conditions that were described before. So it shows also, depending which additive you are adding, you either can suppress space charges, or you're having a higher addition, you actually add their space charge. Again, coming here now, we're going for leakage current, magnesium oxide, different temperatures. Different temperatures, and depending over the electrical field, you can again, it shows that there is an optimum how much you should add. So here it's depending where you would like to operate them. The leakage current, it's had a higher effect at 70 degrees, for example, than at 90 degrees. Here's a linear effect, whereas at 70 degrees there's not a linear effect. There's an optimum with 3 pHR. Oops. We're having the breakdown strength at the DC now, and also here you're increasing the breakdown strength with an optimum as 3 pHR of magnesium oxide. I must say magnesium oxide there was more focus on that because there are commercial XLPE formulations that are installed using magnesium oxide as a space charge reducing or HVDC additive. Showing you a little bit, the studies were done. These were done at the University of Graz, and they were presented at the G-Cable, where the DC cables were tested over a longer time under DC voltage, making actually a faster PQ test that was described in the TV 496, and giving you and showing that you can use these cables perfectly for these applications. Here is a short summary or sneaky peek, and I'm just looking now and I'm perfectly in time because there's a short sneaky peek about the electrical properties depending on the addition of recycled materials of AC insulation and AC breakdown. So the addition was here, and there will be more, like I said, in that secret paper that will be presented beginning of November. So what was done here was of new, not used polypropylene cables. A certain percentage of recycled material has been added to afterwards virgin polypropylene material, and a new cable was produced. So naturally at 0 you had 100%, and here was a significant drop in it, which we assume that due to the cutting we had metal contamination in the polypropylene. So for insulation compounds, to add polypropylene again as insulation into low voltage cables, that's up to a certain percentage, up to 10%, it's still possible, but then you have to be careful because you are degrading it probably due to metal contamination quite heavily, and it's not recommended. Where we looked was then into sheeting compounds, and we also looked into filler compounds when you're looking into low voltage. There it's easy, you can just replace whatever you want with it, but in sheeting compounds, you can go higher. So the elongation at break and shore will not change at all. The elongation at break and the stress cracking will be reduced if you adding more than 25% of it. which when you're looking at recycled material is already quite a high value. Show you at the end a little bit. This is an installation in the field, as you can see, in China, and it worked. So at that time it was 5 years. At the meantime we had 7 years. So Prismin has 45,000 system kilometer installed. Proudest Eiffel Cable, that's my company. So I have to make a little bit PR. We were number 2 with a cable maker who has installed a cable on the market, and that's what I'm very proud of, because you're speaking with 100% of the development capacity of Eiffel Cable, and so there's no lab behind that. What you can see here, when not down there, the guy actually here, when he was down there, he was up to here in water, so the cable is actually installed submerged. To summarize that, there are several insulation systems based on polypropylene on the market, and 4, according to my information, are installed in the network. The 4 different suppliers have installed cables in the network. 1, and already for more than 15 years, I think we are coming close to 20. Today we have different systems that are developed, which for the utility makes it a little bit more challenging to understand what's going on. And so in general, nobody can say anymore a standard polypropylene cable has been used, because now it's definitely a lie. It was already a lie before when you use it for XLPE, but so it will be short. But PP, we can easily adapt to the needs of the application, where it's needed and what is needed. And just having some legal things. And now, if you're having some questions after you had a couple of beer or a night's sleep, and then you are there, because I could see that there were certain Chinese names, so they're probably, I hope you didn't fall asleep, and you can send me an email afterwards. Okay, that was my thing, and I think I'm good in time.
Yeah, you're good in time, Detlef. Thanks, and very good presentation, and very informative presentation. So we got a few questions here, and I'm gonna read the questions. You can find them on the chat box. You probably need to share your screen also. Some of the questions they specify the presentation, so you can share your screen, Detlef.
Okay, wait a minute. Okay, it should be again. Is it there?
No, but that's okay. I will go ahead with the questions.
Okay, go.
Yeah, the first question is from Sat. It's about the breakdown measurement and breakdown values you reported. Have this AC and DC breakdown tests undertaken on cable specimen or on thin films? Also, have you considered any humidity test?
Both. Wait a minute. Now I need to flip. So this one here.
We don't see your slide, Detlef.
Okay, wait a minute. Okay. Wait, why is it not breaking? So Jesus, it was working by the idiot. Did I get? It tells me I cannot share.
It's coming now.
Okay, it's coming?
Yeah. It goes again.
Okay, but nevertheless, in order not to lose too much time. So all the tests that I have presented here, when we're saying AC breakdown, they are showing Bible. There's even written there, it's a certificate, were done on cable. So they have been done on cables. The development trend tests that are in there. Yeah, okay.
I can share it for you. Do you see it?
Yeah, I see it. So let's say that when you see a Bible distribution of it, then we have done the testing on cables. When it's done under development, the headline was development tests, then the test was done on blacks. HD 605 and 1407, all the tests have been done on cables and under wet conditions, because by definition, HD 605 and 1407, you're making a wet aging test. I hope by this I've answered that question.
Okay, yeah. We can go to the next question from Greg T, my former colleague. Thank you for the great talk. Do you see a need for thermal conductivity while maintaining electrical insulation in the cable?
The biggest issue is actually at the moment we need long-term. There are several possibilities under evaluation, improving the thermal conductivity or improving it, going to the same level than XLPE, and we are working on that. The biggest issue that we have currently is cost. It should not be more expensive. The electrical properties we can keep, the thermal conductivity, but we're getting too expensive because there's some, I would say, funny compounds that have to be added. And naturally, we need a long-term evaluation if it's really necessary.
All right. Yeah. Another question from Diana. Could you expand on the labeling PPC, fully recyclable, and if there is any impact on thermal history on the electrical performance for medium voltage or high voltage application?
And I must say, till now, we have not looked into medium voltage and high voltage. The studies that have been done, and like I said, they will be presented. I didn't want to prejudge for a presentation that will be given in November at SIGRE. I might recycle that presentation at one of the upcoming ICC meetings. We have looked only into low voltage application. Nobody has, I would have stomach pains, honestly, if I'm using recycled materials in a medium voltage and definitely a high voltage insulation compound directly. I must honestly say that. In sheeting, less, and we are looking into it, and we have not actually pulled cables out of the ground and recycled them because that's too young for it. What I know that it can be used perfectly for other plastic applications. So Prismin has used it for, I hope I'm allowed to use that name. They have made presentations we have used it for pellets. I mean storage pellets.
Okay. All right. Another question from Jean is about the carbon footprint. So the question is, do you know of any study to estimate the carbon footprint of PP insulation material when compared to traditional materials? This may be attractive as we move to carbon sustainability.
Yes. Again, the PEEP company has made a presentation at an answer at the SIGRE Symposium in Paris, I think 2019. Stefano, they have done comparing the carbon footprint with that. And also, we have given a paper together with Rosendahl, but that's in the language of Goethe, in German, at the Technical University of Energietagung in Graz, where we looked at the energy consumptions of comparing polypropylene with XLPE.
All right, good. Another question from Igor. Thank you for presentation. The threshold for space charge was established for which temperature? So I see you show threshold of space charge. Was it at room temperature, I guess?
That was room temperature. If there's nothing written, it was room temperature.
Yeah, another question from Enrique. Could you address ways to improve thermal conductivity of PP and which method was used for obtaining the data you showed in the presentation?
That presentation, actually you have, a plug in between two heating equipment and just the temperature difference method in there. Therefore, you also see at 90 at 100 degrees, because my personal feeling is that the pressure could not be obtained with polypropylene at that temperature. So we had variations actually in the measurement system, because we changed the crystallinity, but it was done by the thermal differentiation methods.
All right. Another question from Herman. What is the main failure mode for the PE and PP variants? I guess this is very extended question, but I don't know if you can give some general comment maybe.
And the main failure method is actually in cables is actually contamination.
Mm-hmm. Yeah. Another
Or
question. Yeah.
in the cable, actually third-party damage. The famous digger that lifts the cable.
So during installation, you mean?
Not during the field operation, that suddenly somebody lifts the cable because the digger there was no problem, there was some third-party damage in principle.
All right. Another question from Ido. The volume resistivity of PP showed a great stability along the temperature increase. How come did the leakage current in the later sheet show the opposite current incline as a function of temperature?
Good question. I don't know. Honestly, I don't know.
Yeah, when I see the resistivity and temperature dependence for PP and XLPE, the PP was very stable.
Yeah, but I don't know. I need to look in detail. If you send me that person's email or coordinates, I need to look in the papers where I actually got it out. But I don't know. I cannot give you an answer. I cannot even bullshit about, because honestly, I don't know. I need to check in detail the paper and how it was measured.
Okay, yeah. I will leave your email address on the chat box, so if they need, they can reach out to you.
Yeah.
Okay, another question from Robert. What method and chemicals do you use to color the insulation during analyzing of water trees?
For XLPE, it's methylene blue. That's quite easy. That's known. And for polypropylene, methylene blue doesn't work. You have to use rhodamine.
Okay. Another question from Werner. On slide 36, you showed an increase in ACBD by up to 30% by blending PP and PE. How is that possible, as earlier it was shown that both have the same breakdown strengths?
Due to the when you do a mixture, it's not you have an optimum when you have an optimal mixing ratio between two different polymers. So it's not when you adding A and B together that you only can get the same value. There isn't. I have to use that way. There is an optimum that they mix perfectly at a certain ratio. A specific polypropylene with a specific LDPE, if you mix them together, you have an optimal mixture and they will just fit to each other, and then you have optimal electrical or mechanical properties.
All right. I think that's pretty much all the questions we had here on the chat box. If anyone wants to be unmuted and want to ask a question, please raise your hand. Okay, we got another question. You showed a short circuit test of a cable at 250 degrees C. How is that the test feasible as the TM of PP is above 160 degrees C? So the melting temperature of PP is above 160 degrees C.
In 5 seconds, you don't melt polypropylene.
So it was a very short test.
So the short, let's say you make a short circuit, and always there the maximum time for a short circuit, which is already in the standards, is 5 seconds. In reality, it's milliseconds, point something. You don't operate a cable at 250 degrees. Because also for LDPE, the rated short circuit temperature is, I think, 170. I wouldn't sign that because it's 170 degrees, whereas LDPE melts around 90 degrees, 98 degrees. So also there, you can use an LDPE cables as rated short temperature significantly higher, because in 5 seconds, you don't reach the temp, you don't have any melting. It needs more time.
Okay, I just unmute you, Warner, if you want to ask him.
Yeah, thank you. Siegfried Wender from University Erlangen-Nürnberg. I have a follow-up question to that mixing of polyethylene and polypropylene. So you hinted towards a synergistic effect for the blend at an optimal composition.
Yeah.
And do you have an idea for the model that's behind it? Because this is, yeah, that's what everybody wants, you know. If you're mixing two components and then you get synergy.
I'm always a practical engineer, so I'm not looking at the models. I'm looking at what practical is happening. So, but like I said, what you have to do is you have to look at a specific polypropylene with that specific LDPE. You have that synergy effect at 30-40% or whatever was in the presentation. So I don't know any model behind it because that needs to be studied and at another level. So I'm a more practitioner. So it works, and if it works, it's good. If it doesn't work, then normally I'm trying to investigate what did I do wrong.
Okay, so it's basically empirical. What
Yes.
you found? Ah, okay. So for me as a university guy, sounds very interesting to get the model behind it.
I'm a trial and error guy.
Mm-hmm. Okay.
Fair enough. Yeah. One last question, Detlef from Olan. How does the PP maintain its mechanical strength at high temperature, maybe higher than the melting temperature, caused by some failure to avoid thermal deformation?
Let's say that if you're going above the melt temperature for a longer time, we have done a practical test by accident. The material will XLPE will burn and polypropylene will melt. So it doesn't. If you're going over the melt temperature for an hour or two, you're losing the properties. So there is the insulation just drops off the conductor.
All right, I think we are right on time. 1 hour since we started the webinar. So thank you, Detlef, and thanks for all attendees. I think this is the second highest number of attendees we had since we started this webinar. We have, at the beginning, we have like around 92 people attending. Of course, at the end, people are dropping, but yeah, sounds good. And thank you, Detlef. The webinar will be available on our LinkedIn page. Once the speaker signed the copyright form, we will distribute the recorded version to attendees and the presentation also.
Okay, you send it to me and I will do that. And yeah. Hopefully to see a couple of you in a couple of weeks I think a couple of you I will see in New Orleans.
Yeah, in the ICC and CIDP. So I post the speaker email here. If there is any follow-up also, you can follow with the speaker. Thanks so much. That concludes our webinar.
Thank you. Bye.
Bye-bye.